pleasure to meet you.
No, I cannot. Okay. Can you hear me now?
Yes.
Okay.
Yes, yeah. Just it was the message that they are starting recording the meeting.
Okay. Perfect.
Greg, do you think we can start or we have to wait more time?
Some people are still joining.
Yes, the number is increasing. Yes, the number is of people connecting is increasing.
Maybe just one more minute and then we can start.
Okay. Okay, I think we can start with this introduction. It's really my great pleasure to introduce Professor Gustau Camps-Valls for his second keynote of the conference. He is a full professor at the University of Valencia, and where he is the head of the image and signal processing group. His main research is in developing machine learning algorithms for geoscience and remote sensing, where I think his research is a milestone for the area. And he is the author of more than 200 journal papers. This is a very impressive number. More than 200 conference papers, 20 international book chapters. He edited 4 books on kernel methods and deep learning. His index age is 71 today. This is the last information by today. And there is a paper on kernel-based analysis that is considered one of the fast-moving research, front research for the community. He received the 2 different ERC, one in 2015 and the second one in 2018. Both are related to research in Earth analysis, modeling, and machine learning application to this context. And is from 2016 is one of the prestigious IEEE distinguished lectures for GRCC. So really, it's, I think that we have one of the most qualified researchers for machine learning and remote sensing, and we are very happy to host his talk.
Thank you very much for the invitation. Thank you very much for these very nice words and introduction, Annalisa. Good afternoon, everybody. Today I'm going to talk about recent advances in machine learning for the earth sciences in general that we have been proposing in the last years. Let me start with a very brief overview of the scenario where this work is placed on, and then we will move to the algorithms themselves. Of course, as you can tell from the title, the presentation will involve machine learning, but also the particular characteristics of and challenges as well in the Earth system science. The Earth, as you know, is a highly dynamic, networked, and complex system. And in the last few hundred years, the human activities have precipitated enormous changes in this system. It goes without saying that nowadays, one of the most important challenges that we as scientists are facing is that of quantifying, but also understanding the processes occurring on the Earth. And quantitative, but also qualitative assessment and modeling has a great impact. And assessing how the system evolves through time and space may have very important, very challenging, and very impactful societal, also environmental and economical implications And in particular now, with the growing demand of biofuels and food, we actually want to do inferences on the system. And for that, we use Earth observation data and also automatic machine learning algorithms. We want to do inferences in the Earth system. And for this, like clinicians, we measure again, and check the hypothesis and confront data with models. We use Earth observation data acquired by satellites, along with in situ observations on the ground, and we compare our measurements to what the physical models say, and try to find patterns and vital signs with statistics and automatic machine learning algorithms too. Earth observation in general, or Earth observation data analysis in particular, mainly serves two big purposes, which in machine learning we know very well, either classification or regression. These are like the standard paradigms that we often tackle. We either may want to detect or classify objects and changes, or rather we are interested in real quantities and aim to estimate parameters describing the physical phenomena that we observe on the ground, in the oceans or in the atmosphere, like measuring temperature or the vegetation status. For tackling all these challenges, remote sensing and Earth observation has met like new friends, new colleagues in the last decades. Nowadays, nothing is actually possible without the contribution from many different fields, from not only physics, ecology, and biology, like traditionally has been the case, but also from engineering, computer science, and statistics too. And probably the most contributor in the last decade has been machine learning, and probably that's why I'm here, right? Let me just summarize in just one slide what is machine learning about, and how do we want to do inferences by using this machine learning on the Earth system. So essentially, machine learning can be casted as a general problem in statistics and almost in philosophy too, about learning a function, an arbitrary function that translates some observables X, in our case, these are the satellite images, into a target quantity Y. That can be, for instance, a class label for the image or the pixel, or a real variable for the ground. The key thing here is that this function F has been, well, has to fulfill some characteristics. It has to be nonlinear, mostly it is the case of being non-parametric, very flexible, and most importantly is learn from data. And what I found very peculiar in this arena, at least, is that most of the times you find that the community has evolved to a family of methods, a family of functions, in which little prior knowledge is actually typically exploited in the functions. We only rely on data and data alone. Well, it goes without saying that deep learning, for instance, and machine learning in general, they are advancing the fields of sciences and of earth science in particular. And these techniques allow us to solve challenging problems like classification, regression, anomaly detection with unprecedented accuracy. Advances are so many and the applications are so exciting nowadays that people have even advocated that the AI is, relying of course on big data, is replacing science at some extent, and also education. Well, implicitly, a blind deep learning approach to whatever problem assumes that when enough data is observed, there is no need to understand the physical principles that are underlying your system of interest, which after all, they are just a prior belief, a regularizer. And it is typically claimed that data acts itself as an efficient regularizer. However, is this as simple as that? Well, the point is that the success of deep learning methods is not incidental. Deep learning works very, very well in this perfect storm. Data exhibits some regularities first. Spatial and temporal strong autocorrelations, like in video, image, and speech processing, for example. And that's why it also works very well in earth sciences. The second point that I want to stress is that typically you observe very good performance when you have big data readily accessible, when one has also huge computational resources available and fast and scalable models. And thanks to the new infrastructures and also the democratization of machine learning, this is now possible too. And last but not least, you can observe that 99% of the applications, automatic machine learning is desired. Practitioners just want to reach high accuracy levels with a minimum effort, and if possible, automatically, without taking care of prior knowledge and not even taking care of the explanatory potential of machine learning models. Well, I'm not such a big fan of embracing that philosophy, though. Now the question is, if our nice little object called Earth has all these ingredients and we can continue with this business as usual. Let's briefly review the main challenges that we observe in the Earth system science. Well, Earth observation problems are naturally framed in these big data challenges. We are all aware of the 4 V's, so volume, velocity, variety, and veracity. And in Earth observation in particular, we are observing that data, for instance, now it is actually exceeding hundreds and hundreds of petabytes, and the growing is quasi-exponential. Although also the rate in which we are acquiring data it goes at very high frequency with many different sensors. So the diversity is also involved here. We are acquiring a lot of data sources that are multidimensional, spatially integrated at very different scales, from organ level, let's say leaves, to a very complicated and broader levels at a global scale, for instance. The uncertainty of the data, it's also a very important issue here. And can stand for observation errors, or also can construct inconsistencies in the data that we have to deal with. But most important that all this variety of challenges, of big data challenges, we should not forget about the 5th B, the value. We want to retrieve information. We want to retrieve knowledge out of the data analysis pipeline. Well, there are also statistical challenges too in this arena. I'm not a computer scientist, but a physicist by training. So I really care about the mathematical and statistical properties of the objects I work with. There are some challenges that Earth observation data is introducing, which are more exciting in my view. For instance, we often deal with multidimensional data, either because we want to combine different sensors, or because the structure of the manifold where the data is embedded into is really complicated and nonlinear relationships emerge. Also, non-Gaussian distributions are in the wild, and these statistics actually give rise to data misalignments and distortions. A machine learning algorithm trained in one region, for instance, or in one instant, may be completely catastrophic in another one. And that's why feature representation and adaptation of the domains is a must in our field. And at the same time, we often face the challenge of including irrelevant features. So we want to remove the most irrelevant one, just consider the important, most informative ones. Also, we encounter uneven distributions and all kinds of anomalies in the wild to learn from. And finally, even more, we want to learn a machine learning model with normally very few labeled examples, and then we pretend that we can extrapolate well to unseen data. These are the most important statistical challenges, actually, and they are important ones indeed. And last but not least, this is the family of what I call the real, or if you allow me, philosophical challenges. The field of deep learning in particular is facing important challenges that cannot be resolved with more data and faster computers, but with brains, hypotheses, and domain knowledge. The vast majority of deep learning models do not respect the most elementary laws of physics, like the mass or the energy conservation. They don't know anything about that. And this is actually really, really annoying for us. Also, it has been argued that deep learning models just fit. They excel into that, there is no doubt. But nothing fundamental is learned in the end. Actually, these models are becoming so big and complicated that interpretability is often compromised. And finally, the third point that I want to raise here is that these methods undoubtedly capture some sense out of the data, but how could we actually know that they capture anything about the cause and the effects? Did deep learning models learn anything at all? Are they interpretable semantically, and more importantly, are they interpretable causally? Well, the answer to all these 3 questions is no. Machine learning and deep learning are excellent interpolators, but do not understand the physical mechanisms underlying. With all these challenges in mind, this is the meeting for today. I will try to revise like around 20 new methods that we have been developing in the last years to cope with different, the previous challenges and the previous observations. First, respect the data structure and feature characteristics. Second, try to work with millions and millions of data points in the cloud. Third, respect the laws of physics. And fourth, I would like to put attention into understanding rather than just modeling, and understanding the machine learning models, also encoding and inferring, if possible, laws of physics from the algorithms. Well, Earth data comes in distinct data structures. So either a spatial temporal, or even graph-based. Let me start with machine learning algorithms that adapt and respect this structure of the data. I will introduce methods for doing classification and also regression. Let's start with the data classification first. Well, in current times, exploiting temporal and spatial correlation is best done with neural networks, also in this field. What we call deep learning, or more specifically a method called convolutional neural networks, this is the standard paradigm nowadays in remote sensing data analysis. These convolutional neural networks models exploit the spatial redundancy in the images by learning optimal filters on the image plane only. And optimal in the sense that the resulting features are quite discriminative. Well, when you're dealing with time, and we are all continuously dealing with time series as well, the information is better treated with recurrent neural networks that capture memory and temporal redundancies very efficiently. The combination of both allows you to deal with spatial temporal signals, as we often have in this field. For instance, here, we have been working on convolutional/recurrent networks that account for space and time relationships, and that they excel, for instance, in detecting clouds. Clouds are not only showing some spatial features in the image plane, but also they move, right? And we exploited this particular characteristics of the clouds for detection. But also we want to continuously update land cover maps from remote sensing satellite time series, and this has enormous implications both economically and also in terms of environmental mitigation of climate change too. Well, even when space and time are considered altogether, the vicinity where these models look at, it is actually quite limited. On the one hand, convolutions and memory units are by construction filters with finite impulse response functions. And on the other hand, recurrent and LSTM networks cannot remember longer sequences. So the memory and the persistence of the processes is not optimally accounted for. Several architectures currently try to tackle this kind of myopic problem of neural networks. Promising architecture combines standard ConvNets with human attention mechanisms in neurosciences. So these so-called attention networks can look at the information in distant regions, driving the processes and activations in a local window. Attention networks have excelled in classification problems, but they have been limited applied so far in Earth observation data analysis. There is a wide range of possible applications for these networks. In Earth sciences, one typically requires or acquires data and works with normally sparse, discontinuous, and not necessarily gridded images or gridded spatial, temporal, and stationary data. And these particularities call for models able to work in non-Euclidean domains. Deep learning defined over graphs and manifolds is actually very complicated, and mainly because, you know, it's like we are kind of forced to work in non-Euclidean domains, and that's pretty hard in order to define, like, you know, proper and basic operations like the convolution that it is pretty well defined in the image plane, and these operations are rather elusive. Well, in this arena, geometric deep learning extends these deep learning operations over graphs and has given rise to convolutional or recurrent neural networks that can work over graphs, and this has opened a wide range of applications recently in order to do line cover, class classification, and identification of changes and anomalies too. And in remote sensing data processing, we are very often confronted with problems of heterogeneity of the data. So data acquired by different groups, by different sensors, or in different situations. If you want to put everything together and train your favorite algorithm, that will cause a lot of problems because there is a lot of distribution mismatch. Should we just include everything in just one big database, or rather, can we develop methods that can learn the interactions or interrelations between the individual data sets and sources of information? Well, this is a field that we know very well. It is the field of multitask learning. And here the algorithm may learn the implicit relationships between the features of the different observational sets and combines everything into a, let's say, in an optimal way for classification. Well, interestingly, this multitask learning allows you like two very nice properties. The first one is that you train a model in one situation and and this model is actually very easy to be adapted to another slightly different one. We will see in a moment a couple of algorithms for doing so. And the second point is that you learn the graph that relates the different sources of information, and this is very valuable. Remember that in this field, we are even more interested in learning, in understanding things than just fitting, okay? And now let's move, let me jump to maybe my favorite scenario in the last decade, that is of regression and function approximation. Here in the community, we typically refer it to as parameter retrieval. Recently, many exciting developments have actually appeared in this community. Machine learning is now able to generate what we call products, that is maps or useful information out of the images. For example, neural networks are now vastly applied to create and update land use and land cover maps as well. There is a company called One Soil Maps does this. Also, Digital Globe, now converted into a company called Maxar. It's a company that trained a neural network along with very high resolution imagery and census data. And they were able to create a model that could predict the wealth and the poverty in a neighborhood. There are many different applications in the wild. So just follow these links and you will discover that most of them, they just boil down to solve a statistical regression problem where you have X inputs and Y outputs that you just want to approximate, okay? However, in the remote sensing arena, we are formally setting the problem or framing the problem as a standard forward and inverse modeling. In some cases, we are interested in running a forward model, the so-called radiative transfer model, that mimics how our system behaves. But this model can be very computationally costly to run. And very often, we also want to combine RTMs, these models, with observational data together. And even more common, we want to do the model inversion and find this function f that retrieves some parameters describing the Earth cover or maybe the atmosphere or the ocean or water bodies from these satellite observations X here. Let's take a look at how things are done in our community so you will get some inspiration. When the target variable is a real variable, of course, we're in a regression setting. Let me briefly explain how things are done here in practice. In this case, we conducted what we call a terrestrial campaign, and we took samples or measurements of two parameters of interest, leaf area index and chlorophyll content in plants. And that was actually done at the same time a hyperspectral sensor overpassed the area. After many corrections of the inputs and output data, we basically end up with an input-output training data set so we could run our favorite algorithms for doing regression. And in the last years, you observe that neural networks and Gaussian processes have actually excelled in doing this regression very, very systematically well. Here we train a GP, a Gaussian process, which also provides us with not only with good performance, but also with confidence intervals for the predictions, as you can see in the maps on the right here. So the products that we generate are not only explicit maps of these two quantities, leaf area index and chlorophyll content, but also confidence maps that one can threshold or analyze in detail. Well, in this particular case, since we didn't measure these parameters in bare soils for obvious reasons, I mean, in the end, we were interested in monitoring the vegetation, not the soils. The GP model was not really certain in those region fields. So you can see this in outstanding particular pixels in the image. So you can threshold them or downweigh the relevance for the further analysis. But we can go global too, not just in a particular region of interest. And this exercise was actually done with data coming from flux towers. And we wanted to upscale globally key fluxes in combination with remote sensing data. Well, we took data coming from eddy covariances that are basically sensors mounted on some towers around the planet. And these sensors are actually measuring or estimating turbulent exchange of CO2, latent and sensible heat, and also energy balance. So you can actually estimate out of that the GPP, the gross primary productivity. So basically related, a variable very important for monitoring our planet, that it is actually related to how much carbon the vegetation, forest, plants are actually absorbing. These are these are important variables that we want to estimate, and we identify them as Y. The network of flux towers is called FluxNet. So there are like 200 something towers around the globe, and they are, as you can see here in this map, unevenly distributed, mostly in the northern, richer hemisphere. And as input data, we took some data from a sensor, a satellite sensor called MODIS. This sensor basically covers the planet weekly as a weekly resolution, time resolution, and allow us to estimate very sensible parameters to monitor the flux uptake. We estimated different expressive features out of the images, and we used that collocated with the measurements in situ in the towers to develop different algorithms. For instance, we developed a plethora of neural networks, kernel methods, decision trees, random forests, and in the end, we observed that they more or less perform very similarly. But in some particular cases, they show some discrepancies. So we decided to perform an ensemble with all of them. Well, now that you already have your algorithm trained, with a new incoming observation from the satellite sensor, you can actually generate especially explicit maps of gross primary productivity. And this is actually the combination of different maps of interest. So latent heat, sensible heat, and radiation. They are very important to study the seasonality, interdependencies, also anomalies, and limiting factors of vegetation growth and health and the status, for example. And here's at the point where real science starts. Well, but what happens if you want to exploit, as in the classification scenario, this spatial temporal structure of the data? Well, spatial temporal analysis is actually the commonplace in many different fields: climate informatics, neurosciences, video processing, natural language processing as well. And in all these cases, we have an object that evolves in time, and we want to do inferences about this object, estimating, characterizing, or predicting its behavior. In remote sensing, we have like the big fields of parameter retrieval, time series, gap filling, or also a traditional field called data assimilation, in which models and observations are mixed together. Well, in the last decade, as it occurred also in the case of classification here, neural networks and GPs have excelled too here, mostly because, well, in the case of neural networks, they exploit very well the spatial context, while on the other hand, the combination with GPs, they exploit they approximate the problem under a Bayesian framework, and they allow you to do inferences with, the confidence intervals for the predictions, automatic ranking, and many different properties that are really appealing. Well, I want to introduce here like two different developments that we have been working with. The first one on the left, it's called distribution regression. Here we have many observations associated to an output scalar. So we are no longer working with a one-to-one mapping, but we have a distribution and a scalar. So for instance, we have many pixels in a county or a region for which you want to actually estimate a crop yield, okay? So the method called distribution regression is based on kernels and exploits all the feature relations in the distribution, summarizes the distribution in a very high dimensional Hilbert feature space, and then uses that for doing a standard linear regression in Hilbert spaces. This has yielded very excellent results in this particular problem of crop yield estimation. The second one on the right-hand side of the slide is the natural extension of standard GPs to deep GPs, okay? So here you have a bunch of connected layers of GPs. They are stacked. And we typically apply like different or similar tricks to those used in our networks, yet with the additional advantage of a Bayesian treatment of the problem. So here with deeper GPs, we can actually reduce the error of temperature and also humidity to lower than 1 Kelvin error, since several 100,000 data points can be actually used as in a very similar fashion as it happens in or we have observed in the most traditional deep neural networks methods. And now I would like to end up with this problem that we often encounter, in which regression models are also interesting because it allows you to tackle multi-output estimations simultaneously. We want to estimate different variables at the same time very often. This is very powerful and computationally convenient. In the figure on the left, you can see here, I'm showing you like the result of convolutional neural networks that exploit not only the horizontal axis, so let's say the spatial domain, but also the vertical features in order to estimate atmospheric parameter profiles. For instance, we are now able to estimate temperature at different layers across the atmosphere from infrared sounding data. Interestingly, since spatial and vertical features for temperature are very similar to those for moisture, we actually were able to use the network for doing kind of a transfer learning. With very minor retraining of the last fully convolutional, fully connected layer, we converged to a very good network, very good result for moisture, departing from one network trained for temperature. And this is very important for us, especially now with this huge data deluge, actually, so we can be more efficient and reuse what we have already learned from previous methods. Well, there is also, as I told you at the introduction section, that there's a lot of concerns nowadays about the efficiency, right, and dealing with big data challenges. Let me talk a bit about efficiency, not much because it is not my field of expertise, but I have a friend here that knows a little bit. Yes, you guessed it right, is Google. And Google created the Google Earth engine when you can actually develop algorithms in there and you don't have to worry much about the data processing, because all the data from NASA and ESA and many different sensors and collections of data sets are already in there in the platform. This is for free, so you can operate and code your algorithms online without too much worries. So let me just show you some kind of cool applications that we have been developing in the last years. The first one is a kind of a joke for us. It is cloud detection in the cloud. Okay, so why clouds? Well, clouds are really important, a really important aspect in remote sensing. Clouds are basically covering our planet around 70% of the time and locations, which is very critical for optical remote sensing because you cannot see the ground and you cannot operate and deliver products, but also for climate sciences, since it leads you to a lot of great uncertainty in knowing how much radiation is actually reflected by the clouds. So you cannot actually quantify very precisely the warming of our planet. So cloud classification is actually a very active research area. Typically, researchers develop algorithms that look for white, bright, and dense textures, but clouds also move, and we have a wide range of cloud types as well. So here we exploited this capabilities of the Google Earth engine to exploit the temporal information. So the algorithm actually was able to do a simple one-step ahead prediction of the next scene from the previous clean ones. Okay, so you identify some clean images before, and then the algorithm just do kind of a predictive model to predict the current scene, which basically is intended to describe the background. And then you just compute the error, and then that accounts for associated, well, that can be associated to changes or more intrinsically associated to clouds. Well, the second application is not about classification. It is more about regression. And we wanted to generate global maps of key vegetation parameters. In this work, we took a vegetation model in home, ran it to generate simulations with all possible parameterizations, trained a random forest to invert the model, and implemented that in Google Earth Engine. Well, with the proposed methodology in this paper, we can actually upscale to global scale almost any variable that we encounter in sensible radiative transfer models. And in this particular case, this is the first ever map of canopy water content derived, of course, from a model. The third one is also about specializing a big database. Imagine that you have a big database with tons and tons of data. In this particular case was the TRI database. It is for plant traits. And well, after many different steps, fusing of different sensors with climatic data, we were able to generate global maps of plant traits, never seen before, like nitrogen or phosphorus rates, and all of that just purely based on data. Okay. Finally, an example that we have been developing recently basically considers the use of meteorological but also climate variables that one can estimate using satellite imagers directly in a model to estimate indicators, whatever indicators you may think of. Here we implemented a COVID-19 transmission intensity model that was published in the literature that essentially relies on temperature and relative humidity. And this particular model was actually calibrated against 100 cities in China. We simply implemented this in Google Earth Engine and upscaled this kind of relationship globally. And well, of course, other models are possible to be implemented. You have to take into account that they should rely on meteorological or climate variables. Well, a kind of disclaimer here, we only implemented this to allow users to assess the claims about meteorological impact on COVID-19 spread, and hopefully will help modelers and experts in the field to test their hypotheses on models. By no means we want to suggest that this model is perfect or has we don't even want to mention whatever implications of the model. Okay, so far so good. The previous models and implementations work very well in practice in principle, but something is missing. And note that in standard machine learning, as I said before, the function f is learned from data and only from data. Well, this is true until now. The truth is that we need to live in a kind of interplay. Models without data are pure fantasy, and data without models are kind of chaos. In recent years, there's a high interest in combining purely data-driven machine learning with physics laws and constraints and hypotheses. And the gains are multiple: consistency, sufficiency, but also speed, of course. Let's summarize what's all about and in a set of recent developments that we have been proposing. Well, there are many different algorithms out there. Let me start with this simple example to incorporate physics in machine learning. This is the field of constraint optimization, a very standard field in maths and statistics. The idea here is to include an extra regularizer term that minimizes not only the error, but also the sum of all impossible solutions guided by the physical model. So in the toy example in the right-hand side figure, well, the authors wanted to estimate the temperature at the different depths layers, in particular lakes. And they managed to impose the known relationship between the temperature and the density as a kind of constraint optimization problem where one minimizes all these discrepancies, or let's call it inconsistencies. Okay. Well, a second approach to combine machine learning and physical models is to define the relation explicitly in the algorithm. In this case, we develop a model that we call multitask or joint GP. And this model combines two kernel functions, one dedicated to observations coming from the satellite observations and the other to radiative transfer model simulations. And what it is nice of this model is that it learned the relative relevance of each term, and it compensated the lack of knowledge or measurements or in situ measurements in the real world and filled in this space with simulations. We apply that to estimate a particularly interesting parameter, the leaf area index, which is basically the amount of leaves that you encounter in a square meter. And for that, we use satellite data from Landsat and also simulations from a particular model called ProSail. Well, we observe like better accuracy, but also consistency between models and data. And also being a GP, one retrieves more credible confidence intervals, but also very nicely, a kind of indicators of extrapolation regimes. Okay, so when you are actually outside the in-sample region, and so you can actually tackle that prediction accurately. Well, the field of hybrid machine learning is actually becoming kind of quite mature, actually. And there are some examples of encoding prior knowledge inside the machine learning model itself, not just like a constraint optimization, as I said before. We have recently reviewed in this Nature Perspective paper the role and challenges in deep learning, how integration with process understanding is, in our opinion, the way forward. On the left-hand side, you have a general framework to, let's call this, physicize a deep learning model by including constraints in the form of network layers itself, not just as an extra term in the laws. While on the right-hand side, you see a particular example of how things are done now. So essentially, you have a deep learning model that can learn the motion fields, okay? So it is a sequence of different acquisitions, and that they are kind of accurate, but also physically consistent because you are adding an extra layer that kind of warps the motion field estimates with a physical model. So you basically distort your predictions in order to fulfill some properties of physics of the motion fields. So what it is also nice in this hybrid modeling is that with automatic differentiation schemes, you can actually learn end-to-end the network. So you learn the network parameters, the weights, and also the physical model parameters too, and all from data. Well, and another exciting field nowadays is that of replacing physical models with machine learning. This is called emulation or surrogate modeling. This morning we observed, we attended this very nice talk on surrogate modeling. And here we just want to replace your costly physical model with a machine learning algorithm. For that, you basically generate a bunch of simulations and treat this as a standard regression model. I want to emphasize here that it is not only a question about of gaining in speed, but also gaining in tractability and sensitivity analysis. So understanding things, because if you apply a GP instead of a regular random forest or neural network, which are kind of opaque, you can actually derive automatically sensitivity analysis, and also you can retrieve confidence intervals for the estimates of the spectrum. What it is interesting here on the right-hand side, you see some figures, some rankings, some ranking plots of the spectral channels most impacting the model. And you can hardly say or hardly differentiate the different rankings if they are coming from the actual simulations or from different machine learning models. This is nice because that means that the emulators, the surrogate models, actually encapsulated the physics pretty nicely and efficiently. And finally, I would like to mention an important problem that we often encounter in our field is that of learning parameterizations. So learning about the prior density of the parameters that we want to deal with. So in this work, we learned those parameterizations, the densities in an RTM, in a transfer model, in a physical model. The model gives a Gaussian likelihood, and assuming a Gaussian prior, we want to fit essentially or learn the prior parameters. Well, the point is that integrating with the RTM, with the model inside the Gaussian mean is really tough though. But this can be actually solved pretty nicely with variational inference. We essentially introduce the variational posterior into the log marginal likelihood, then chose the variational posterior to be Gaussian, which mean and covariance are learned with a neural network. And since the Kullback-Leibler divergence between two Gaussians is easy to compute and derive with respect to parameters, we can actually compute the expected value of the log likelihood. Well, there is a distinct feature, a distinct difference here. Unlike in traditional literature of variational autoencoders, we here are placing a deterministic forward model instead of a decoder network, and fixed a low value of noise variance in the likelihood in order to reflect that we actually trust the forward model. Well, the convergence time of variational autoencoders here in this particular scenario were orders of magnitude faster than more traditional or exact methods, or based on Monte Carlo approximations. And moreover, you can actually have access to the mean and the covariance function, so you can actually sample and use that as a method for inversion and to generate like estimates of particular parameters in the model. In this particular case, we actually were interested in again, vegetation parameters like canopy water content, the chlorophyll content or concentration, sorry, or the dry matter content too. So we could actually generate maps out of that, distributional maps. Right? Okay, cool. So far so good again. It looks like we are getting closer to an agreement between these two, in principle, irreconcilable communities of physics-based and computer scientists. Well, the previous section tried to incorporate this prior knowledge or domain knowledge in machine learning and to design models that are kind of consistent with our deep understanding of the physical processes. Now I want to pay attention to a more complex scenario, that of understanding rather than fitting. And yes, I don't have a formula to put there because there is no formula to express what knowledge means, right? Well, there are different approaches in this community. The first, most important, or the most standard one, to understand what the model, what the machine learning model has learned, is essentially look at feature ranking. Okay, so we are well equipped since decades with techniques that can discover or can rank the features of the covariates, that can quantify the informative content, and that ultimately return a ranked list of descriptors. Okay, that's fine, but this is kind of naive, especially now with this growing number and complexity of the different models that we are working with. And actually with bigger and more complex models, we are kind of lost track of what models have actually learned. So we have now techniques to analyze what's important for the model in both space and time. On the right-hand side here in the slide, for example, you may see the result of a deep network trained to predict crop yield. So how much is going to be the production at the end of the year, the harvest time. And what times and scales in the whole time series are really important to do so. So in this particular case, we use standard visualization techniques of the neurons and help us to readily get some insight on model weights. For instance, we have now techniques to analyze this in a very sensible manner, and you can readily identify that essentially the network is paying attention to peak slopes, to high derivatives of the time series, and also, most importantly, to the region of the growing season, what the farmers identify as the standard growing season. So it is pretty nice that the algorithm, without even prior knowledge, could actually identify those regions. That's important. Well, and finally, I would like to point towards what I think it's my opinion, the most interesting field in machine learning and statistics nowadays, that of learning causal relations from data, or from observations, but not only from observations, which is pretty difficult or not even impossible, but also from hypotheses and from prior knowledge as well. So the goal here is to jump from a mere ranking of relevance to a kind of graphical model that describes the underlying mechanisms of the problem. And from a set of variables, causal discovery essentially learns which are the cause, which are the effects, and ideally when and where those relationships, those cause-effect relationships happen. This can be very useful for three main applications. The first one is, of course, hypothesis testing. Okay, so you have an hypothesis about how the system is working, and you want to check that hypothesis purely based on data. Also, there is a second application, a very important one for us, which is about comparing models and data, because we often just believe what the model has encoded itself, and you believe the model, but maybe it would be really nice to confront what the model is actually modeling with the data, that is basically the observational truth. And also, that's the third application. It is about relying on causal discovery methods in order to assess the causes of extreme impacts. And this is actually a very, very important, and you know, it's still in its infancy, but it is like picking up very, very, very fastly in the domain of climate sciences. Well, we have published this particular paper in which we review all the field, the whole field, and how one can learn causal relations from data and from observations. And here, basically, we identify like four families of different methods: range causality, also nonlinear state-space methods, also methods based on causal network learning, in which you have to rely on specific methods like PCs algorithm, or structural causal models that are really, really useful when time is not even involved in the processes. Let me just give you an example about this, and I will only focus on the first one, the most traditional one, the most traditional method in causality, even though that it is not actually causality. It is called the range causality. Well, here we depart from some global time series of interest, like soil moisture, for instance, and vegetation optical depth. This variable is a recent one and basically captures how much water the plants are actually accumulating. And also we have a third climatic variable that it is called the El Nino, okay, the El Nino Southern Oscillation, ENSO time series, that it is related to that can be related to many different phenomena in the whole planet. So we want to derive explicit global maps of causation between ENSO and soil moisture. And for that, well, as I said, we focus on the framework of Granger causality. And in particular, in Granger causality, one tests whether the past of X is useful to predict the future of Y, along with other variables, which are other variables that may be available. One fits two models. One decides that X causes X, X causes Y, if and only if the error of the first model is lower than the second, okay? So traditional two main caveats, two main shortcomings. The first one is that typically one uses an autoregressive model, so linear fit. The second one, conditional test, is also linear in most of the cases. So here we derive a nonlinear kernel-based Granger causality method that uses obviously a nonlinear regression and also nonlinear conditional independence tests. The kernel function that we actually used can account for different non-stationary processes altogether, which is a third limitation of Granger causality indeed. I'm not going to enter into the details, but I just want to mention that the solution comes in closed form. As in the linear case, it is quite fast thanks to some operational tricks, and it returned very, very nice accuracies, and it was kind of robust to false detections. Well, we studied this relationship between soil moisture and ENSO. On the left-hand side, you can see the lag correlation map, like the traditional thing that the climate scientists do. And on the right, you can see our nonlinear causality method. Both identify similar patterns of wet and dry impacts of El Nino. However, note that many of the correlations found were actually very spurious associations, here indicated in red circles, not causal, which are only a few of them. This is actually the first causal map of ENSO on soil moisture worldwide, which has also important implications on characterizing and anticipating heat waves or floods, for example. Well, I just wanted to promote this field, but also I would like to promote this platform that we have developed in the last year for evaluating causality methods. So basically, authors can download a bunch of time series, run their algorithms at home, upload the solution proposed, and then the system will evaluate and rank the solutions according to the ground truth that it is in the platform itself. Well, and with that, I would like to finally conclude with some take-home messages. Machine learning is now becoming a mature field in earth sciences and climate sciences in particular. The important thing here is that machine learning is a solid mathematical framework. It allows you to deal with nonlinearities, multivariate data, etc. And also, I would like to mention a kind of word of caution. The use of machine learning by non-experts can lead to dramatic failures with high risk of overfitting and overlooking. And the remedies, in our opinion, is basically to stick to these new fields in which understanding is more complex, but also more important than just fitting, incorporating domain knowledge, physics-driven machine learning, trying to explain what the model has learned, and also educating diversity. Because in these three fields, explainable AI, causality, and hybrid modeling, we will need interaction, the tight interaction between the domain experts and the computer scientists. And this is, I promise you, it's really, really difficult to achieve. Finally, I would like to mention that all these activities are also part of our research program in ELIS. And last but not least, I would like to thank very deeply to my incredible team, without whom I'm nobody. They are funny, proactive, and really brilliant. So thank you very much for your attention. And yeah, I'm looking for people. And remember that all models are wrong, but some can be useful.